All right, we're going to look at logic part 2. And what we're going to talk about today is these things called truth tables. So when we look at these Boolean statements, which is really a combination of a bunch of simple statements, remember, using the words and, or not, we like to use this truth table to be able to keep track of the truth values of our simple statements and then use those to look at the entire statement and determine if it's true and false. So suppose that you ask your child what they'd like to do today, and they respond, I want to either play soccer or a board game. In what situations would this child be happy, and in what situations would the child be unhappy? So they're going to be happy if they go and they play soccer, or they're going to be happy if they play a board game. And they're going to be unhappy if they don't play soccer, or they don't play a board game. So it seems like as long as they either do the soccer or do the board game, then they are going to be happy. So when we look at statements involving, basic truth tables for this and, or, and not statements, they're really just summarizing what we already know about the meaning of these statements. So let's write two statements, and we're going to label them P and Q. So I'm going to use, you can use anything that you want. Try and be something different than mine. I like coffee is going to be one statement, and then Q is I want to go fishing. So using these two simple statements, if we want to write what they are, what the symbols mean, remember that we have that upside down V, that means and so we're going to say that I like coffee and I want to go fishing. Now the next one, we have the right side up V, that means or. So we're going to say I like coffee, or I want to go fishing. And then lastly, with our negation here, it means not. So not P would be I don't like coffee. So we're going to use these statements to kind of guide us through these truth tables for those three statement forms, the conjunction, disjunction, and negation. Recall that and statements are true when both statements are true. So the only way that I like coffee and want to go fishing is if that's true, that I both like coffee and I really do want to go fishing. The or statements are true. Let's think about this for a second. I like coffee or I want to go fishing. When I hear that, I know that I either like the coffee or I want to go fishing, maybe even do both of them. And that would be the inclusive use of the word or, which is what we normally will use. Now, I don't like coffee. That one is going to be true as long as I don't like coffee. So let's go through this. So we want to list the different ways that we can have our P and Q. So it could be that they are both true, or we could have that P was true and Q is false, or we could have that P is false and Q is true, or we could have that both of them are false. And so when we look at that meaning of and, if we know that P and Q are both true, then we know P and Q is true. Now, if we know P is true and Q is false, there's no way that the and could be true. And so that would follow for the next one, and the last one is for sure going to be false because neither of them are true. For the disjunction, we're going to fill the table out similarly, putting all the different ways that P and Q could happen. And this is kind of the standard, that P is kind of split in half, like true, true, false, false. And then the next one alternates true, false, true, false. So now we're looking at or. So if both P and Q are true, then of course the or would be true. If we're using that as the inclusive or, which we are. Sometimes you might see a symbol like this, which would be exclusive, but it's not as common. Okay, so now for our second row, true and false here. As long as we have one true, we're going to be true. And so that follows for the next one. And then the last one, they're both false, so there's no way the or could be true. So that will be for sure false. And lastly, for our negation, we're just looking at one statement, P, and then comparing it to not P. And negation really means opposite. So if P is true, then not P would be the opposite. If P is false, then not P would have to be true. Now we're going to combine those simpler truth tables to something a little bit more complicated to figure out in this situation when it will be true or false. So the situation we have is not P and Q happening. So let's list our possibilities again. We like to go like true, true, false, false for our first row, our first column. Then we'll alternate for our second column. So now if we're going to negate P, then we're going to have to look at P and do the opposites. So that's going to end up being false. And then for the next one, false. For the next one, true. For the last one, true. Since negation means take the opposite. Now we're going to look at the negation of P and Q together. That's the ultimate final result that we want. We don't know when this thing's going to be true or not. So we're going to look at these two columns, and again, we're looking at a conjunction. So in order for a conjunction to be true, both of them have to be true. So T and F together, that's going to be false. Those are for sure false, looking at those together. True, true, that would be true. And then the last one would be false. So these are the truth values for that bigger statement. And so it's always going to be false. If you kind of want to go back to our original, if P and Q are true, then this statement's false. If P is true and Q is false, then this statement is false. If P is false and Q is true, then this overall statement is true. And if those both start out false, then that conclusion there also comes out to be false. All right, now this one has a third statement in it. So just a reminder, kind of going back to our counting, if we want to see, you notice that this is a lot longer, their columns are longer, it's because there's more ways that we can have this P, Q, and R. So there's really two ways that the P statement can happen. There's two ways the Q statement can happen, two ways that the R statement can happen. By the fundamental counting principle, that gives us 8. We're going to need 8 rows. And so you can come up with a pattern to try and list all these possibilities. Normally what happens is that we, under the P column, we're going to just split that in half. So we'll have 4 trues and then 4 Fs for false. And then our last column for R will alternate. So that should be similar to how we did it on the last one. And then the Q, just again to make sure we get all the different options, we're going to go true, true, false, false, true, true, false, false. And you can see that every one of those combinations is different. So again, that's the standard way that we normally write those. So now what we're going to need to do is to negate that column P, so that whole thing. So all those trues become falses. All the falses become true. Next, we're looking at the conjunction of not P and Q. So we're going to look at the second column with that fourth column. And when we put those together, remember conjunction means both need to be true. So T and F together, that's going to be false. T and F is false. False and false is false. False and false, false. Lots of falses. Then we'll have a T and a T, that's true. T and a T, another true one. And then a false and a false. Next, we're going to negate R. So we're looking at the R column and we want to negate it. So true turns to false, and this is on the alternated. So we can just alternate these. False, true, false, true, false, true, false, true. And so our last thing that we'll need to do then is to look at this combination. So we want to look at the P and not Q. So we have that here. I mean, not P and Q. And we want to combine that with the statement R. Now this time though, we're looking at that statement or that statement. So as long as either one of them is true, then we'll get a true value. So false, false means that we're going to be false. False, true will get us a true. False, false will be false. False, true will get us a true. We get another true, true, false, and true. And so these are the truth values for that more complicated statement. All right, and so lastly, we're going to look at two laws. These are De Morgan's laws, and what they do is they show you that the negation of a conjunction is actually equivalent to the disjunction of the negation of the statements making up the conjunction. So if we have the negation of that conjunction, you could see it changes to a disjunction where each of the parts get negated. And then similarly, this will happen when you negate a disjunction. It'll change to a conjunction of the negation of those statements. So that negation ends up switching out to a conjunction, and then you get the negation in there. So it kind of looks like distributing, but it actually changes from a conjunction to from a conjunction, yes, to a disjunction, and then similarly a disjunction to a conjunction. And so we're going to use truth tables to prove why these statements are actually equivalent to each other. And so we're going to start by filling in the things that we know. We're talking about statements P and Q, so we're going to start with that. When you look at what you need to know, we need to know the conjunction. So we're going to put P and Q, and then we'll be able to negate that. And for the last part, we need to know what our negation P will be and what our negation Q will be. And so we're going to go true, true, false, false, true, false, true, false. Again, that's just getting all of the different ways that P and Q can happen, kind of systematic there. And so P and Q, only the first one will be true because you need both things to be true. And so if we negate that, we're going to have a false, and then the rest will be true. For not P, we're negating those P's, so it'll be false, false, true, true. And for not Q, we're going to negate Q. That'll be false, true, false, true. And then we want to look at those two together. And when we look at those two together, with a disjunction, we want at least one of them to be true. So false, false ends up making false. False, true ends up making true. True, false makes true. And true, true makes true. And so the way that we know that De Morgan's law is actually true is by looking at this column and that column. And if they have the same truth table values, then what we say is that these two statements are logically equivalent. So their outcomes are the same, depending on what the P and Q are. Sometimes you'll see this notation, right, like 3 bars to show that they are equivalent. So we can say that the negation of P and Q is equivalent to the negation of P or the negation of Q. And so we're going to do the same thing in this chart. If you followed along with the last one, try and do this one all by yourself. So it starts again very similarly. We need to know P and Q. We're going to need to know P or Q in order to negate it. And for the last one, in order to do that conjunction, we need to know the not P and not Q. So truth table here, we'll go true, true, false, false, and alternate for the Q. And so for or, remember for disjunction, it's true as long as one of them is true. So those are both true, so we'll get a true. We have at least one true, and then false. So then its negation over here would end up being false, 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 true. And then to negate the P, again, we're looking at that first column and doing the opposite. So it would be false, false, true, true. And then to negate the Q, it'll be false, true, true. And so if we combine those together, that not P and not Q, that will be true only if both of them are true. So false, false will get me false, false, true will get me false, true, false will get me false, and then true, true will get me true. And so you can see right there that this column is the same, has the same truth values as that last column. And so we're going to say that these two are going to be logically equivalent also. And that's really proving De Morgan's laws. And so we know that the negation of P or Q is equivalent to saying not P and not Q. Now, we proved it using these truth tables, but like, what does that really mean? Let's think about it, and we're going to go take one step back to writing two sentences for those statement forms. So let's look at statement 1. And I want to come up with a P or Q. Let's say that, again, we're looking at saying that this is equivalent to this. So if I say it's not the case that it's raining and hot. So you can see my statement here. You see it's not, so that's our negation. It's raining, that will be our P, and hot is going to be our Q. And it said it's not the case that, meaning that it's not the case and everything that follows. So that's why I put those parentheses on there. And so then for that second part, we're saying that this is going to be equivalent to saying that it's not raining or it's not hot. And so the reason why that's coming out that way is because when we say it's not the case that it's raining and hot, like it's not raining and hot outside, but it could be that it's just not raining or it's not hot. It's just that it's not both. And so that's how those are equivalent to each other. So let's try that again for the second part. So for this one, we're looking at negating the P or Q. So let's think about another statement. Let's say that I don't like soccer or baseball. So I don't like soccer or baseball. And so then we're saying that that's equivalent to saying that because this negation, and then we have our soccer or baseball. So we're going to say that I don't like soccer and I don't like baseball. Because you're like, I don't like soccer or baseball. Okay, I don't like it. And then you say, I don't like soccer and I don't like baseball. That's equivalent to saying that.